Chapter 14, Kinetics, Exercise 14.71. The tabulated data shown here were collected for the following first-order reaction from A to B to A2 and B. The temperature and the corresponding rate constant are listed in this table. As the temperature increases, the rate constant increases as well, as expected. Part A. Use an Arrhenius plot to determine the activation barrier for the reaction. This is activation barrier or activation energy in kilojoule per mole. Part B. Use an Arrhenius plot to determine the frequency factor for the reaction. The frequency factor denoted by A is also pre-exponential factor. Now let's look at part A. How do we determine the activation energy or activation barrier? Over here, we will use the Arrhenius equation. K is equal to A times e to the power of negative E sub A over RT. But we can't use this equation directly. We need to take the logarithm of both sides. So what I will do is I will just copy paste this, and then I'll put Ln K here. And it's going to be Ln A and then minus EA over RT. We'll use this equation. Now you can see Ln K is proportional to 1 over T. So what I will do is I will copy and paste the data to the Excel spreadsheet. Let's see if we can do a copy paste. Delete these 2 rows. Alright, and somehow this one is not considered as a number. For some reason. Alright, and this is good. This one is not good, and there's extra rule. Delete. Alright, this one is 3.72 times 10 to the power of negative 5. Alright. Line all the way to the right. Okay. Now what we need to do is we need to have 1 over T as the horizontal axis. This one is in Kelvin to the power of negative 1, so sometimes people just write 1 Kelvin over T to make it unitless, and then Ln K here. But if you're careful, you want to do Ln K times second just to remove the unit before you take the logarithm. So let's do this. It's going to be 1 over temperature in Kelvin. You have 1 over T, and this column should be the logarithm of K multiplied by the second, just to get rid of the units. And we have 4 numbers here. This simply means this is not treated as a number, so I need to retype this. Alright, now we have a number. This was not treated as a number somehow because of some invisible characters. I need to retype this. Alright, now we're good. We select 4 data points and insert a graph, and we'll then do linear regression. That's it, to determine the slope. We have a graph here. Ideally we should format the axis so it's not wasting a lot of space, but okay, let's just focus on tackling the homework problem. First we need the slope. So we do plus trend line. Don't check this yet, just do this, and more options. And right here we can just keep this linear and display the equation. R squared is equal to 1. Very good fitting, perfect fitting, or nearly perfect fitting. And we have the slope. The slope is, if you look at this, the slope is negative activation energy over R. So EA is equal to, here's my equation, negative slope times R. Alright, or you can say slope times negative R. Either way you want to do, I mean, it's the same thing. This is the equation I'm going to use. Why is that? Because by looking at this equation, you realize the slope is actually negative EA over R, the gas constant. Alright, from this equation you get this equation. And now we have the slope. The slope is negative 28747, and multiplied by negative R. We'll get this in joule per mole. Because if you look at the gas constant, it's 8.31446 joule per mole Kelvin. Of course, you can easily convert it to kilojoule per mole, which is this number divided by 1,000. 239 kilojoule per mole. It's a very large activation energy. So it seems that okay, this is actually not very common to have a activation energy more than 200 kilojoule. Alright, so over here. There's another way to get the slope. I want to show you how to get slope. Equal slope. This is one way to get the slope of a linear fitting directly. You just need to highlight the vertical axis, and then comma, and then highlight the horizontal axis, and then that's it. You get the slope. Oh, I'm sorry, we need to switch this. We need to switch this, I believe. Slope here. Sorry about this, I forgot to use L and K versus 1 over temperature in Kelvin. Alright, so that was a mistake. Now I got the slope, and if you compare this slope by using the slope function with the slope in the graph, negative 28747, negative 28747, they are the same. They are the same. And also this slope times negative R, we'll get this in joule per mole. In joule per mole. All right. Now let's look at the intercept. There's the intercept. The intercept is L and A. So I will just give you L and A. L and A is the intercept. 25.735 is 25.735. All right. This is the intercept. And you can see the intercept is L and A from this equation. L and K is the vertical axis, 1 over T is the horizontal axis. Therefore, negative EA over R is the slope, L and A is the intercept. Alright, actually it's L and A times second is the intercept, because the vertical axis is actually L and K times second. But anyways, A is going to be e to the power of that. The function in Excel is exp. Alright, it's a very large pre-exponential factor, 1.5 times 10 to the power of 11. In Joul's general chemistry book, this is called frequency factor. It's honestly not a very good name, because this is actually not proportional to the frequency after you study chemical kinetics in detail. But anyways, I'm gonna call this pre-exponential factor, 1.5 times 10 to the power of 11. Alright, so again the equation is negative equals exp, which is exponential, e to the power of L and A, which is the intercept over here. Submit. Alright.